All right, so we continue with Möbius transformations. Yeah, which is I don't know. I find it a little bit like a Ravel's Bolero, which is like you have some very basic melody that starts repeating over, but kind of in a more powerful way. So at least, yeah. So it's kind of a more or less what comes to my mind. So we're going to start describing what will play the role of the circle centered at the origin, that played a role for certain Möbius transformations, and these are the Apollonius circles of 2 points. So for 2 distinct complex numbers, and each fixed R, this set, the set of all the z's whose quotient of distances to the 2 given points is constant. So the ratio of those distances is constant. So the set of all points in C bar whose ratio of distances to the 2 given complex numbers is constant is a circle. Here I take topological closure, which is kind of only when R is 1 is this topological closure needed. So notice when R is 1, I'm speaking about the set of points whose distance to W0 is equal to the distance to W1. That's just I think it's called the mediatrix of the 2 points. And then since I actually want a circle in C bar, then I close it topologically to just include the point at infinity. But otherwise, for other choices of R, this set is already closed. And the theorem, the result is that these sets are circles in C bar. Yeah, for each R. The proof is not hard. You can see the whole computation here. Kind of the way one comes up with the proof is pretty much noticing that here inside the absolute value symbol, what you see is a Möbius transform, the expression of a Möbius transformation, and we know that Möbius transformations send circles to circles. So the rest is just unraveling that and pretty much seeing exactly when you send one of them to 0 and one of them to infinity, like here, exactly what circle center at the origin corresponds to this CR. So which would be, here is slightly, I switched the roles of R, and but anyway, this is then you can just see the proof, and it's pretty much routine exercise. Okay, the Apollonius circles. So each such is called an Apollonius circle of the pair, and they are going to play the role of the circles centered at the origin, and then in case this is when both of my points are in C. And then one says, okay, what if one of them is infinity? What if one of them is infinity? If one of them is infinity, we actually already know what circles I want. Just the circles centered at the finite point. Those are the Apollonius circles. So the circles centered at the origin are the Apollonius circles of 0, infinity. Now, yesterday we also had,
Sorry, this is a stupid question.
yeah,
Can we see, do you have a picture?
yes. So,
Maybe it will come later.
no, it's good that you tell me now, because, for instance, let's see 0, 100, and I'm going to show, let's say 99 Apollonius circles. Okay, maybe that was too much. Yeah, sorry. Let me clear. Maybe let's say just 0, 1 and 25. Yeah, sorry. Yeah, and they look like this. They are not really tangent, as you can see. Like somewhere inside here is 0, as you can see from the kind of the projections, and somewhere inside here is 1. Yeah, and those are the Apollonius circles of, these are 25 Apollonius circles of 0 and 1. That's how they look.
So 0, 1 being the 2 points that you choose.
Yes. Here, these are my 2 points that I chose. Yes. By the way, and it's good that you mentioned, because now I'm going to about the loxodromes. So parentheses. Yeah, this is a loxodrome. In this case, okay, I have not defined them right, but for 0 and 1. But let me put, okay, this is a loxodrome for 0 and 1. The ones from yesterday, let me write here infinity. Yeah, so that's a loxodrome for certain choice of alpha, for certain choice of angle. And let's say, I don't know, 25, right? And then here you can see, this angle is equal to this angle. It's kind of equal to this angle, equal to this angle, equal to this angle, etc. So it's at least visually more or less clear. Yeah, and then let's change the angle a little bit. Yeah, I don't know, maybe like this. Yeah, and then yeah, so you can see. Yeah, so maybe let me try to do something a bit more exaggerate. Yeah, so that you can see that actually, when I change the alpha, the angle actually changes. And here you are seeing that my way of drawing I'm using very few points to actually draw the loxodromes. Yeah. So yeah, and yeah, loxodromes are not polygonal, but yeah, yeah. But so at least it's kind of, you can see how the angle between the loxodromes and the circles change as I change the complex number alpha. Okay. So let's go back. Yes. Yeah. Okay. Okay. Parenthesis closed. Right, and then remember that yesterday, like in every situation, we had 2 families of curves. So now, if I give you 2 distinct points in C bar, we have one family, which is the family of Apollonius circles, and this family again foliates C bar minus the 2 points. By foliating, I mean vaguely, but I mean that each point in C bar minus those 2 points belongs to exactly one of the curves I'm talking about. Okay, but there's the other family I need of curves that I also have to talk about, and this other family is the family of common circles. So the family of circles that pass through my 2 given points. And then these 2 families are going to work for certain Mobius transformations, and then for let's say for the elliptic and the hyperbolic, which, if you remember, those are the ones that are conjugate in MEB C bar to multiplication by either an element of the circle, -1, and or a positive real number, -1. Yes, for those we are going for those two types of Möbius transformations, we are going to be using these two families: the family of Apollonius circles and the family of common circles. And we are going to call the family the pair consisting of both families is the Steiner grid of my pair of distinct points in C bar. And now for the parabolic Möbius transformations, which, if you remember, are those that are conjugate in MÖB-C to translations, which are in themselves Möbius transformations with infinity as the unique fixed point, so that in the end, parabolic Möbius transformations are those that are conjugate in MÖB-C bar to sorry, excuse me, going back. Parabolic Möbius transformations are precisely the ones that have exactly one fixed point. Okay, for those I need a degenerate configuration, like I need some sort of degenerate Steiner grid, and a degenerate Steiner grid at a given point. To define one such degenerate Steiner grid, what I do is I take, at that point, I take a tangent vector and fix that direction, and then take the orthogonal direction. Yeah, this in the tangent plane to C bar at the given point. So that given point here would be W0. And then what I do is I take the first direction that I pick, the first direction that I pick, and I form the family of circles that are tangent to that direction at W0. So maybe let me write this. So I have W0 here, and then the family is the family of circles that are tangent to this. Okay, those don't look like circles, but somehow you get the idea, and they don't even look tangent at W0, but okay, but you get the idea. So that's one, the first family, and the other family of curves is the orthogonal one, which is, maybe let me change color here for the other family, is orthogonal here, and then it's again all the circles, and that's not even tangent. The circles that are tangent to that direction at W0, at W0. And this I call a degenerate Steiner grid based at the given point. And of course, given there's a slight distinction between the situation of two different points and only one point. In the case of two different points, the family of Apollonius circles and the family of common circles, it's like uniquely determined, whereas here is uniquely determined by the 2 points, whereas given 1 point, there is not one degenerate Steiner grid based at that point, but infinitely many, because I have to give you not only the point but the tangent vector. Yeah, so that's kind of one point at which the notions are a bit different. Yeah, and as I said, the degenerate ones are going to help me to study the parabolic Möbius transformations. Yeah. So here I stop very quickly just to say Möbius transformations are conformal. Yeah, and actually this can be shown like by hand. If you take a Möbius transformation at a point, let's say a complex number, a point in C which is not infinity, and just let me take a point different from the point where the denominator is 0, and then one can really compute the derivative as in Calc 3, as in third semester of undergrad, if not before. And it turns out that the tangent plane has the structure of a complex vector space, dimension 1. Yeah, and the derivative is simply multiplication by this non-zero complex number. The derivative at the point, and multiplication by a non-zero complex number preserves angles. So it's conformal. Yeah, and then one can play around to see, okay, what happens in the two special points you have not analyzed here, namely infinity or where the denominator is 0. That's an easy exercise. Yeah? Like even what I said here is just an easy exercise. The kind of the short way of doing it is saying, okay, P1 C or C bar is a Riemann surface, and one can check that Möbius transformations are holomorphic maps of C bar, right? Yeah. Okay. Now the thing is, okay, how do you check that? Well, you have to take at some point just the derivative. I mean, you have to do it by hand at some point. Okay. Anyway, the thing is, since they are conformal, they preserve oriented angles between curves, between, let's say, curves of class C infinity, just to be on the safe side. And this I'm going to use to transport to define a degenerate Steiner grid for parabolic transformations, yes. So it is for a parabolic transformation. Yeah. So namely one with exactly one fixed point. I know it's conjugate to a translation. So let's say that I take tau in Möb C that conjugates it to a translation. Yeah, and here it is. You asked yesterday at some point when I said they are whatever they are conjugate, and he asked, okay, he said like, but in Möb, right? And then yes, and it's very important that it's in Möb, because then we know that the conjugating transformation preserves sends circles to circles, disks to disks, and being a Möbius transformation is conformal, so there's nothing to worry about. Yeah, and so the degenerate Steiner grid of this parabolic transformation nu is defined as taking the kind of the obvious degenerate Steiner grid of the translation by this vector beta and transporting it to nu and its fixed point. Yeah, so the thing is, the idea is for translation by beta, we saw that there's the family of curves. There's the family of Euclidean straight lines with direction beta. So direction the angle of translation. and those are straight lines that foliate C bar minus infinity. Okay, so I take those and I transport them. You know, I map them via tau inverse. Yeah. And similarly, you know, yesterday we saw that also given a translation by beta, also there are many families that are of straight lines that are permuted. Yeah. So among those, I take the special one, which is the orthogonal to beta, and I map that one to you know, via tau inverse to obtain a degenerate Steiner grid, and it's a degenerate Steiner grid because in the case of translation by beta, both families consist of circles in C bar. So when I apply to them tau inverse, what I have is circles in C bar. And let's say the family of straight lines parallel to beta, in C bar, they have only infinity as common point. So when I apply a Mobius transformation to them, they will have only one point in their images are going to have only one point in common. Yeah, but you see, the correspondence is that infinity is sent to corresponds to the fixed point of nu by the construction that we did yesterday, which means the straight lines parallel to beta are mapped to a family of circles, all of them that are pairwise tangent, and they are tangent at the fixed point of nu. And if I take the other family, the family of straight lines orthogonal to beta, same thing. They are circles in C bar, so they are mapped to circles in C bar by tau inverse. They all share exactly one point, namely infinity. So tau inverse of them share only one point, namely the fixed point, because again the shared point was infinity. So, like the fact that yes, sorry, and they are all based, or all the circles in one family are orthogonal to all the circles in the other family because tau and tau inverse preserve oriented angles. Yeah, so it's kind of everything fits to see that that I have two families of circles that are pairwise orthogonal, and each of the families foliates C bar minus the fixed point. Right. See, yeah, and maybe something that I should have written here is that this tau sends the fixed point of nu to infinity. So maybe I should write this. So yeah, tau of the fixed point. Bless you. I'm going to have to write this. Yeah. So for a parabolic transformation, it's Steiner grid, which is a degenerate Steiner grid. Bless you. Always looks like you are seeing here, and if you map it to the sphere via to the unit sphere via the stereographic projections, you are seeing how it looks like that. I mean, the family of red ones was not completely drawn, so, but it would be, you know, I mean, I think you can imagine them, right?
So this is one of those degenerate Steiner grids that we defined earlier, but it's a specific one. So the tangent vectors are chosen.
They are actually determined by
this beta.
No, they are determined by nu.
Right.
That's actually an exercise. Yeah, it's an exercise from the series of exercise from last lecture, from not yesterday, from Wednesday. That it's it's independent. It's independent on. It depends only on nu. Mm-hmm. But it's a good point. Yes. Yeah. So each parabolic nu has an associated degenerate Steiner grid, which is well defined, dependent only on nu, not a one parameter family. Yeah, and again, this is simply because conjugation just kind of transports the behavior. That's why each member of one of the families is stable under the action of nu, and more accurately under the action of the subgroup of MEPC generated by nu. And this is because we conjugate in order to see the picture in the situation of a translation, so sending the fixed point of nu to infinity, so that the conjugation is translation by beta, as we said, and then the vectors parallel to beta. Sorry, each line parallel to beta is preserved by translation, is stable on their translation by beta, and then kind of we unconjugate, if you want, or however you want to call it. The point is that conjugation is like just transports the behavior to the situation you are interested in, and same thing with the other family. The other family comes from the family of straight lines orthogonal to the vector beta, and this set is permuted by the action of nu, and conjugation simply transports this behavior to the situation we are interested in. So somehow here the idea is that one of the two families you are seeing, it happens that each curve is stable under the action of nu. So it's something like if you pick a point there, then its image is also there, then the image of the image is also there, the image of the image is also there, etc. You see, and moreover, since it comes from taking a translation and conjugating it, if you think about a translation, it's kind of translating along beta. It's kind of, it comes from infinity, getting away from infinity, and after some time, it starts getting close to infinity, which means that for a parabolic transformation with a finite fixed point, if you pick a point, you start applying your transformation, and then it starts getting away, but at some point it has to start coming back to the point. Yeah? And by the way, here the dynamics I drew was counterclockwise, but it could be clockwise as well, right? I mean, for instance, nu inverse is a parabolic transformation, which then has the kind of the opposite property, right? So there are parabolic Mobius transformations whose dynamics, about kind of repelling infinity first and then coming back to infinity, repelling the fixed point first and then coming back to the fixed point, could be as well clockwise. So that I'm not asserting anything. Whereas the other family gets permuted, right? So for example, in the first situation where in the first where I took the point, and then I said you know, it's image, and somehow I depicted a counterclockwise behavior. So what I'm saying is that like for the other family, this one gets mapped to another one like this, right? And then somehow the image of this would be this, and then the image of this one would be this one, etc. And then at some point it starts converging to on the other side, yeah. And then that's kind of how they get how the other family gets permuted. Yeah. Okay. Yeah. So I did something really simple, which was your transformation. Look at the fixed point. Take a Mobius transformation that sends it to infinity. This was my tau. Conjugate by that one, and then you already know the behavior for a translation by whatever vector beta. Just map it back through tau inverse. Yeah? So I did that. That's it. I did something really simple. And now the Steiner grid, yeah. And at some point I do want to show you some animations, but maybe let me deal with the Steiner grid of a non-parabolic, and then we see some animations. I'm going to do the same thing, but for the Mobius transformations that have two fixed points. So it's kind of you can already imagine what I'm going to do, and then you can just say, okay, then just keep going, right? Skip the slides, but yeah, but you know, humor me, please. So I take a non-parabolic transformation, not different from the identity, right? So non-parabolic. Yeah, okay, yeah. In any case, there's a if here, so no problem. Yeah. So the Steiner grid of a non-parabolic transformation is going to be in the case if nu is elliptic or hyperbolic. So if nu is conjugate to multiplication by an element of the circle except one, or to multiplication by a positive real number except one. The Steiner grid is just the family consisting of the Apollonius circles and the common circles to the 2 points. Yeah, and if it's loxodromic, if nu is loxodromic, what do I do? Well, you know, I simply conjugate by a Mobius transformation that sending one of the points to 0, the other one to infinity, so that the conjugation itself is multiplication by some alpha outside the circle and outside the positive real ray. And you see, what do? I take the loxodromes that I already had, and then I map them, and it should probably be tau inverse, because you see, if here it was tau inverse, here it should be tau inverse. Yeah, because tau inverse sends infinity and 0 to the fixed points. Yeah, so here's tau inverse. Yeah, here it should be tau inverse. Yeah, and yeah, because now I want the behavior I knew, map it through. Yeah, so here's tau inverse. Okay, but you see, there I was already, here I was already shameless, right? I mean, I just said, okay, just take what you know and conjugate it. Sorry, not conjugate it, just map it back. Yeah. Whereas here I was a bit more subtle. Okay. And the result is, well, again, what should the result be? If I take a rotation, then for each Apollonius circle, which is a circle centered at the origin, well, rotation preserves it. So for an elliptic transformation, each Apollonius circle should be preserved. Okay, and again, in the case of a rotation, the common circles are the straight lines through the origin, and each such straight line under rotation is mapped to another such straight line, which is another common circle in C bar through 0 and infinity. So what happens for an elliptic transformation? The set whose elements are the common circles gets permuted. Yes. Let me finish describing the result, and then we can see some animations. If nu is hyperbolic, so multiplication by a positive real number different from 1, here, when I take an Apollonius circle, the Apollonius circle is dilated, right, or shrunk, but so it's mapped to another Apollonius circle. So in the case of a hyperbolic transformation, the set of Apollonius circles is permuted by the action of the hyperbolic Möbius transformation, whereas each common circle is preserved. Yeah? So again, the proof is really just that when you conjugate, the conjugating transformation simply transports the behavior. Yeah? And we are using and if you think about it, we are also using circles get sent to circles, angles are preserved, blah blah blah. Okay, so in a way, the behavior, it's kind of, one can sort of think that the behavior of elliptic and hyperbolic transformations are sort of dual to each other in a way. The family that is preserved the family that is permuted by an elliptic is each of its members is preserved by a hyperbolic, and the other way around. Okay, and now finally the loxodromic ones. Each of the curves that we defined in the previous one, each of these curves is stable under the action of the Möbius transformation, and actually for the Apollonius circles. Yeah, if you consider the Apollonius circles, that one gets that family gets permuted, and simply because multiplying by minus 1 is actually elliptic. Yeah. Okay. No. So because you see, in the case of 0 and infinity, which is multiplying by a complex number alpha, not in the circle and not in the positive ray. in the positive real ray. It does both. It rotates and either dilates or shrinks. So if you take a circle center at the origin, its image, it's not itself, it's another circle centered at the origin, because it's rotated and then a homothety. So the family of Apollonius circles is permuted, and the family of common circles as well, because the image of a straight line is another straight line. And it's not the same line, it's not exactly the same line, because your alpha, okay, you can say maybe negative, maybe the negative, okay, maybe a negative real number, but okay, if it's not a real number, then the line is really another one. If in the case of negative real numbers, when alpha is multiplication by a negative real number, yes, in that case, yeah, in that case, each common circle is preserved actually. Okay, but I think in that case, the common circles are the loxodromes. Yeah.
In the classification of the conjugacy classes.
Yeah. Yeah.
So the multiplication for a negative number
is loxodromic. Loxodromic.
It's loxodromic.
Yeah.
Yeah, this is just not positive.
Yeah, 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 yeah. But for negative real numbers, yeah, what happens is that the loxodromes that are actually just the rays. I think. Okay, no, I would have to think more. I will have to think more. Yeah, I don't want to stop and do it live. Yeah. Okay. So I will continue. In any case, the good thing is that the loxodromic Mobius transformations don't survive when one asks which Mobius transformations are isometries of the hyperbolic plane. So not much to worry about. Okay. And then before continuing, yes, I do want some. So here, so maybe let me start with a parabolic one. So what I'm going to do is, I mean, we know how to picture the degenerate Steiner grid of translations, in particular of translation by one. So the family of curves, each of which is stable, is just horizontal lines, and the permuted one is the vertical one. Well, at least according to the definition of what the Steiner grid is, would be the vertical ones. Okay, so that's kind of boring. So what I'm going to do is I'm just going to take that and I'm going to switch 0 and infinity. And so in other words, I'm going to conjugate this. So I'm going to take this one and I'm going to conjugate it with multiplication with switching 0 and 1 in the obvious way, which is 1 over z, which is its own inverse. Okay, and then I'm going to see the behavior of this one. Yeah? Okay. All right. Yeah. Yeah. So if you do that, the computation, that computation that I showed, what you obtain is 1, 0, 1, 1. Here I'm going to write maybe more points. I don't know, 50. I think for parabolic, this animated orbit doesn't yet work, but this one should work. Okay, sorry, I have to say. I'm not going to take 0 because 0 just gets switched with infinity. Or should I take 0? Let's see. No, I'm not going to risk. So let's take 1. Yeah, okay. No, I mean, okay, let's see. Let's see. No, okay, no. You see, the thing is, you see, there's a little thing here, which is kind of if you zoom out, it stays there, and so it's supposed to be the point at infinity. And then in some animations, I can make it, like boom, like a blink. Yeah. But yeah, but so I think I have not finished programming this for parabolic. Anyway, so let me then go to 1. So where was I? Yeah, okay. So all of that looks there. Yeah. Okay. So now, what should the behavior be? The original one was translation to the right by 1. Yes, and 1 over z. What does it do? It has 1 as fixed point, and it rotates around 1 around the fixed point by 180 degrees. This I would have to prove, but this means that that if I take that behavior and rotate it, I think if I'm not mistaken, that now somehow things move this like clockwise. Let's see. I may be wrong. Okay, so these are the first 50 members for the orbit of 1. Yeah, and now the only thing here, what I'm going to do is I'm just going to move the initial point and see how those 50, the first 50 look like, right? Okay, and then why don't yeah. So you see, I'm moving just the original point, and then then the program is computing the first 50, the first 50 iterations applied to that point, and you can already see somehow that they always describe a circular shape. Yeah. So what circular shape? That one, right? So this belongs to one of this degenerate Steiner grid, and then I can, I continue moving, and then like I move a little bit, let's say, and then I move a little bit, and move a little bit. Yeah, and you can even see, you can even somehow visualize the continuity of the Möbius transformations, because somehow I'm moving very closely, and you can see that somehow these ones somehow are kind of close. Yeah, I mean, I know it's not a proof. Etc. Right? So this is more or less the behavior. I didn't do it carefully enough to see, that then if I somehow if I start describing an orthogonal circle here, then somehow their images also start kind of lying appropriately in circles orthogonal, passing through the fixed point. This I somehow, it's kind of, it's not really, nothing close to perfect. Okay, and yeah, this animation for parabolic, I don't yet have them. So let me clear this. And now let me see. So for instance, let's see. I want. You see here what I have depicted here is the unit circle for elliptics in the positive ray. You see this one moves. Oops, this point. This point moves here, but you see it cannot go to the negative. Yeah, I don't allow it because the idea is that it gives me the parameter, the parameter alpha for hyperbolic transformation. Yeah, and then this one is this other one is if I want to see the behavior of a loxodromic one. So let me see. Let's start maybe with an elliptic one. Yeah. Admittedly, I think this program has floating point problems, and you see here the alphas for which you have a loxodromic one is dense, which means that if you have at least a priori possible that if you have floating point problems, whenever you want an elliptic or hyperbolic, in the end it gives you a loxodromic. It computes you a loxodromic. Yeah. So I cross fingers. Yeah, and then you see I give you this value, but then I have to tell you, okay, what fixed points I want. So let's see these two, and then it computes a matrix. Yeah, that if floating point problems didn't exist, would be the matrix I'm looking for. And now I'm going to start with 0. And I'm going to start here with 50. Okay, I don't know if it's a good example. So, I mean, you can see it describes a circular figure, right? I mean, and it looks like one of the things that we saw as Apollonius circles, right? I mean, that's somehow more or less how they look like. Yeah, so, yeah, okay, so enough. So here, let's move a little bit. Yeah, I don't know. I cannot grab it. I don't. Yeah, okay, and then okay, it's because when it enters the loop, it clears the canvas. Okay. So here you can see. I mean, I'm not saying that the curve is the orbit. No? I'm just saying the orbit lies on the curve. So the curve is a union of orbits. That's what I'm saying. So that's for the elliptic, and you see, let's say here I draw the fixed points. It's in a way it sort of looks like it's rotating around this fixed point. That's actually what happens when we start speaking about a hyperbolic geometry. These elliptic ones are going to be the rotations of the hyperbolic plane around the fixed point that lies in the hyperbolic plane. Okay, so at least here I didn't run into these floating point problems so badly. And now let's say this one kind of close to one. Close to 1 means that I'm not going to explode so quickly. And then I again choose my two fixed points, compute the matrix, and then yeah, I take, let's take 0, and then animated orbit. I mean, and that looks like it's kind of getting away from one of the fixed points and getting close to the other. And you can already see it does look like a circle segment, like it lies on a circle segment. Yeah. So yeah, okay. So maybe let me just do this, the draggable orbit, and then start dragging the initial point. Yeah, let me draw the other fixed point. So you see, I drag the initial point, right? So you can really see that for instance here, what that figure means is that if I start here with this point, it really gives you the impression that it gets away from one and gets close to the other. So let me maybe clear this and then the fixed points. Yeah, so let me start maybe with minus 60 plus 80, more or less. So minus 60 plus what? Plus 80 J. I think that should work. That shouldn't crash. Yeah. So kind of getting away. And kind of slowly for sure, but surely getting close to the other one. Yeah, okay, now, yeah, and then this looks like a circle segment from this point to this point. And you see, this does look like a segment of a common circle. And then you start. Yeah, you can just start playing around. Yeah, okay. And now the loxodromic ones. So let's say I do something like maybe also close to 1, so not so much rotation and not exploding too quickly, or so one thinks. And then I choose the 2 fixed points. And then again, let me start with 0. What did I do? Sorry. Yes, thank you. Yes. Oops. So what did I do? Yeah, I deleted the fixed points. Sorry. Yeah. Okay, and now compute matrix. Yeah. Okay. And now it should work. Why did I draw the invariant curve? Okay. Sorry. Like the plan was to first see compute matrix. Just kind of how it looks like only, right? Yeah, okay, and then now it's kind of boring, right? Everything is just going to be here. Yeah, okay. Yeah, but so you see again, okay, so maybe more clear. That is me again. Compute matrix, and now maybe a draggable orbit. You see, this 0, here is 0, and here are the positive powers, the positive iterations, and then I take that initial point, and then I get it close to the other fixed point, and so at least you can at least this suggests that the behavior is that when you start applying the positive powers, you start getting away from one fixed point and getting close to the other fixed point. which I mean, if you think of the standard examples, it's like, yeah, obviously that has to be the behavior. Because this is conjugate to multiplication by some alpha, and then the positive iterations are start multiplying by alpha squared, blah 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 blah, and then depending on the norm of alpha, that either goes to infinity or goes to 0. So that's kind of the corresponding behavior you are seeing here. And now invariant curve. This, and again, I'm not saying that the invariant curve is an orbit. I'm saying it's a union of orbits. Yeah, and then if you move a little bit, then you see how the corresponding curve moves. Yeah. Okay, and then let's say animated orbit. Where is it? No, I didn't even see it. Ah, there you see a red. Yeah, it's coming out. It's coming out. Yeah. Yeah, it goes here, goes here. Yeah. Okay, and then somehow like it gets boring unless you try to zoom in. Oops. Yeah. Okay. All right. Do I need something more? I think. One more. Slightly different. Never mind about what that 1 and 1 mean. Oh, okay, not do mind. This because here this means in relating it to Professor Tomasi's course, this would be for a Riemann surface of genus 1 with 1 marked point. But seeing the point, she said like a cusp. Here one sees it as a point at infinity. Okay, anyway, yes. So show, yeah, and now if this is well programmed, and so here what we are seeing is the image, for instance, of this point, which would be this point, and the image of this one, which is this one, and the image of this one, which is this one, yeah, under a hyperbolic Mobius transformation that acts as, like a kind of getting away from this point and getting close to this point. So if I now apply you see, the point is there was a so what lies behind this is that I took a hyperbolic Mobius transformation mapping this segment of circle to this segment of circle, and it just sends this one to this one, the Euclidean middle point here to the Euclidean middle point here, and this one to this one. We know that there's exactly one Mobius transformation with that behavior, and I applied it, and I applied it to this blue, funny-looking square, and then when I click on this, what is going to happen is that it's going to be the square that is applied. Yeah. So this is the image of this under the square of the transformation. This one here is the image under the cube of the transformation. And you keep going. Right? And now here the kind of the magic is that it's like, okay, you have to say, okay, stop, right? Stop doing this. So I stop. Yes. But so you see here, you can see that this elliptic transformation has the behavior of getting close to certain point here. Yeah. And by extension, getting away from the other point. Yeah. Okay, so that then you are seeing a hyperbolic transformation that actually also seems to preserve the disk, this disk. Okay, so let's leave it there because yeah, let's leave it there now. Yes. Oh, okay, this went too far. Yeah. Okay. So now I'm going to starting kind of to move slowly towards the stuff I really need for the models of for two models of the hyperbolic plane, which are the 1 second. Sorry, something happened. Yeah, sorry. I don't know why that happened. Okay, anyway, to move to two models of the hyperbolic plane, which are the upper half plane and Poincaré's disk. Yeah, so it's kind of now what I'm having the back of my head is that I'm already starting to trying to locate explicitly what are the Mobius transformations that preserve the upper half plane, which is the set of complex numbers with the positive imaginary part, and I also want to locate explicitly the Mobius transformations that preserve the unit disk in C bar. Yeah. Okay. So some considerations about groups of matrices. So I would say this is a very easy exercise. The inclusion of the special linear group into the general linear group induces this isomorphism. Yeah, and then I would write here, that this by definition is PGL2C, which is GL2C modulo its center, and I would say that this is PSL2C. Yeah, that's easy. That's an easy exercise. I mean, it's like you take something in GLC, take its determinant, and then take that matrix and one row multiplied by 1 over the square root of that determinant. You are done. You see, and you are finding another representative here modulo this one. Modulo that one. No. So it has to be modulo that one. So I think so you divide both rows by 1 over the square root of the matrix. Yeah, and then you get a representative here. Yeah. Okay, now in the real case this fails. You see, so in the real case we would consider the special linear group and the general linear group again, and the induced group homomorphism is easily seen to be injective, but it's actually not surjective, and this is I mean, this is easy, and especially if I just give you a matrix not in the image, right? And pretty much the point is that the trick that works for GL2C may force you to divide by an imaginary number. So it doesn't work for GL2R. Okay, this is really not bad news. This is actually good news. Yeah, I'm not going to say yet why, but it's good. It's good that this is not surjective. The exercise is compute the index. I mean, I guess you can already guess what the index is going to be. It better. Okay, no, I'm not going to say more. Okay, so finally, at least the definition of the upper half plane, as I already said, is the complex numbers, is the set consisting of the complex numbers with a positive imaginary part. For the moment, I take it still with the analytic topology, with the usual topology. Later on, it is going to be a model of the hyperbolic plane. So we're going to give a Riemannian metric for it. This Riemannian metric defines its own topology on U, and it's a theorem that this topology coincides with the usual topology of U. But for the moment, we don't know that. And as I said, I want to locate the Möbius transformations that preserve U. Yeah, and I want those that preserve U bijectively. You know, like a kind of I want to exclude, for example, if you consider, for instance, vertical translations, the image of U is contained in U, but properly. I don't want those. I don't want those. I want the ones that preserve U bijectively. Okay, and somehow the life is more or less fair, because if you give me a matrix in SL2C, so I'm already using the fact that every Möbius transformation of C bar can be represented by a matrix with determinant 1. And this is a consequence of the first fact in the previous one, that this is an isomorphism. So I'm using that, and the statement is for those that have determinant 1. If I don't take it with determinant 1, then some of the things I'm going to say may fail. Okay, but I'm not losing any Möbius transformation. That's the point. I'm still covering all of them, and the statements and the equivalent statements are that A is in SL2R. So you see, if you tell me, if I ask, okay, let's say what are some obvious matrices whose Möbius transformations preserve U bijectively? Well, they have to preserve U bijectively, so by continuity, they have to preserve R union infinity bijectively. So it's like, okay, so SL2R. Those obviously preserve for those matrices. One obviously has that U goes to U bijectively. Okay, one only needs to check that U and minus U don't get swapped. Yeah, okay, one checks it, one just sees, okay, the image of I lies in U itself, okay? And the nice thing is that your obvious guess works, and only those work. So that's the nice thing about this result. So it's equivalent that A is in SL2R, that mu A preserves U, who knows if bijectively or not, but it preserves also the boundary, the topological boundary of U in C bar, which, by the way, R bar, what else can it be but just R union infinity? Okay. So this is like it preserves U, but also you cannot you cannot really like it's kind of you cannot move vertically because you still have to preserve these and they are continuous. Yeah. Okay. U bar is preserved, but again bijectively. Yeah, and U is preserved bijectively. The proof, I would say, it's basic algebra and topology. Yeah, I'm not sure I want to stop and really kind of read the proof because I have 12 minutes. Maybe just say some words, and in any case, the proof is going to be there so you can read it. So the thing I said, like the obvious ones, the ones in SL2R that they preserve, that they have this property. Well, it's obvious that one of these sends R to R bijectively. Yeah, right. I mean, because it's you have to take 8z plus b divided by zz plus d. But now your z is either infinity or a real number, and those guys are real numbers. And it preserves U. Well, what I said, just by continuity, you just have to check that some point in U is sent to some point in U. So you take your favorite one, you compute, and you compute the imaginary part. This is 1, this is positive. Okay, and you keep going. So I'm not sure I want. So maybe I will just skip. Yeah, I don't want to just stop here and just read. Yeah, but okay. So I'll just keep going. Yeah, so the thing is, matrices whose Morris transformations preserve U bijectively, SL2R. Okay, now I'm going to move to try to establish the same result, but for the unit disk, that I'm going to call the Poincare disk. The answer is going to be this SU11. SU11 and not SU11, PSU11 and PSL2R are going to be conjugate in MEB, in PGL2C. Okay, but let me not. But I'm getting ahead of myself. So by definition, SU11 is the set of 2 by 2 matrices that somehow preserve this phony matrix that I'm not sure if people call it J. Yeah, okay, I don't know. Right, where this A star is, as usual, the conjugate transpose of A. Is one of these like classical groups. And then the first order of business is to describe it explicitly in terms of of properties of its entries. So it has this nice description that I'm not going to try to read for you. And the proof, once you know what you want, what has to be proved, it becomes an exercise. So again, I'm not going to read the proof. It's here for you to read. It's very basic. Okay. Yeah. I'm just going to say that. Look, that this equality is just saying that given a matrix of this form, alpha, beta conjugate, alpha conjugate, that its determinant is 1. Okay. So I already told you why I'm interested in SU11, and now what I'm going to do is I'm going to show you one Mobius transformation of C bar that sends the upper half plane bijectively into the unit disk. Now this, we should be able to know how to do it in many ways, because we have the upper half plane, we have the unit disk, and we want to send this inside here. And well, we know Mobius transformations and continuous. We know that in order to determine one, all we need is to say what it does to an order triple. So what I do is I take this this order triple minus 1. So maybe let me write it minus 1, 0, 1. Yeah, which in that order goes counterclockwise, around U, in the circle surrounding U. So all I need is to choose 3 points here in an ordered way, but just going counterclockwise. And if I do that, I will automatically have this whole thing going into this whole thing. So I have many Mobius transformations that send this to this, and they are all easy to find. Okay, so, but I'm going to give only one. Namely, I'm going to pick minus 1, minus I. And notice that going this way is goes counterclockwise. So I know that whatever the computation gives me, it's going to send all this into all this. Because circles go to circles, and because Mobius transformations are continuous. Let me write this. I minus 1 minus I. Okay, but it's already here. Yeah, so this was, my picture was already here. Yeah, and I didn't notice. Okay, and I take that Mobius transformation. It's called the Cayley transformation. I'm going to be calling it Mobius transformation. Well, we know that Mobius transformations are holomorphic maps. So it's this one is a biholomorphism between U and D, and the Poincare disk.
My ignorance, what does
It's just invertible holomorphic, which I'm pretty much saying holomorphic surjective. But if you, the by here, I just put it just to stress the fact that I do cover the whole disk. But of course, I know that once you have a bijective holomorphic, its inverse is automatically holomorphic. Okay, an easy exercise. The Mobius transformations that preserve now my Poincare disk bijectively. Sorry, my wires crossed. In order to find all the Mobius transformations sending U to D bijectively, all I need is take one of the ones I know, one Mobius transformation that does the job, and compose it with all the ones that preserve the one I want to send. So it's kind of a self-solving exercise, right? So yes, so 18/40, and I have 3 minutes. Okay, Now, I want the same for D. I also want to be able to describe explicitly all the matrices that give me Möbius transformation, that give me exactly the Möbius transformations that preserve D bijectively. It's kind of, I already gave you the answer. And the characterization is, if you think, is kind of a copy paste of the characterization of the equivalences, the equivalent statements that I did for U and R bar, but for D and D bar and its boundary, which in this case it's S1. Yeah. And then one can adopt here, knowing the previous theorem, one can adopt two strategies. Either you try to prove it directly, making as if you have never heard about the existence of SL2R, or just say, okay, I already know the other theorem, and I have a Möbius transformation that helps me to conjugate.
Another stupid question. So how do I think of D bar? Because
D bar is the closed disk, the closed unit disk.
Okay, because the pointary disk is the open disk.
Yes.
I
Yes.
see.
Yes.
Thanks.
Okay. So exercise, right? I mean, if I didn't stop to give you, to give you the other proof, why should I stop? Okay, then do this one. Yeah, sorry. Okay, now I have 1 minute. I'm not going to try to keep pushing, but the Minkowski's, the hyperboloid is, I would say, I don't know, one model of the hyperbolic plane that, since now my time is running up, then I'm not going to talk about it. I mean, on Wednesday I'm just going to talk about the upper half plane directly. But Verbung. So the one point is that R3 with Minkowski's form actually gives you a model of Einstein's theory of relativity. You probably know this already, where the space is two-dimensional. And I found two amazing books if you want to dive a little bit into special relativity, which are these two books that I find really, really amazing. Okay, tempo scaduto. Okay, and I don't know these guys, and they have not paid me to mention their book. So see you tomorrow. Not tomorrow. Well, probably, but see you on Wednesday.